Good afternoon, everyone. I'm Ravit Kumar Singh, teaching assistant for this course, Numerical Methods for Engineers, being taught by Niket Kaisare. And this is the third NPTEL session, third live session. And so today I want to start with some basic concepts about systems of linear regression. So in the last class, someone asked me about the geometrical interpretation of uh, various types of solutions. So for example, if you have a unique solution or an infinite solution or no solution for the system of linear regression, how does that how can we visualize that geometrically? So I just want to show you briefly how can we do that. So let's start with simple two-dimensional system. Okay, so we have suppose we have x-axis and y-axis. Okay, and we have two equations which is like y is equal to 2x minus 2 and y is equal to x plus 4. Okay, so hi Tejal, can you hear me? Okay, so did you attended the previous session today, 3 to 4? Okay, okay. So were you alone or someone else also was there? Okay, okay. So has it ended or is it still going on? Okay, okay, okay. Okay, okay. So Vignesh asked this geometrical interpretation in the last live class of the system of linear equation. So I was just trying to explain that, but he hasn't joined. So I thought I'll just proceed and maybe he'll see the recording. So shall I proceed? Oh, okay. Vignesh is there. Hi, Vignesh. Yeah, so like you asked in the previous class, this geometrical interpretation of system of linear equations. So I wanted to give you some basic stuff. Okay, so shall I proceed? So here just I have written sorry two equations. Okay, and so one is y is equal to 2x minus 2 and y is equal to minus 6 plus 1. Yeah, I'll just sorry, this thing keeps happening. Okay, let me start over. Okay, to do okay, let's see. Yeah, so here we have simple two-dimensional system, y and x. Okay, and let's say two equations, 2x minus 2 and y is equal to minus 6 plus 4. Now how can we represent here? What is that? Can you guys wait, let me export it. Let's see, as a PDF, then I think it will be better. Okay. Okay, let's see. Yeah, no, it's fine. Okay, can you see the slides? Can you? Okay then. I think it will be fine. So, so yeah. So let's say we have x and y-axis here. Okay, and so two equations. So the first equation, y is equal to 2x minus 2 is this one, and the second equation can be represented not like this, maybe little bit over, because it's plus 4, so it should go like this. So we'll have a solution here, right? It will be 2 2, I think. Yeah. So similarly, we can have another set of equations. Let's say 2x minus 4 y is equal to 2x plus 1. So here you have a unique solution, right? And in this case, if you will draw these lines here, so y equal to 2x minus 4 will be somewhere here, and y equal to 2x plus 1 will be somewhere here. So you can see this, since the slope of both these lines are same, they will be parallel, okay, and hence there will be they won't intersect anywhere, so it's no solution case. And similarly, you can have another set of equation. Let's say 2y equal to 2x plus 4 and y equal to x plus 2. So as you can see, you can divide this by 2 and you will have the same equations 2 times. So it's just it's just same equation overlapped on one another. See, so it's a infinite solution case, right? This is in the 2-dimensional system. Okay, now when you will go to I mean, it's pretty straightforward in a 2-dimension, but in 3-dimension, in case of planes, it's not that easy to visualize it, right? So I have I have put up a figure here for your reference. So let's say we have 3 systems of linear equations, anything like, sorry, let's say a1 x plus a2y plus a3z is equal to k1. Similarly, you have a4x plus a5y plus a6z is equal to k2, and a7x plus a8y plus a9g is equal to k3. Okay, so you have these 3 systems of equations, and so these 3 equations in 3 dimension will represent a plane, right? Suppose this is x-axis, this is your y-axis, and it goes into the screen, the z-axis. So so these 3 equations will represent a plane oriented in some direction. It can be I mean, that depends on these coefficients and this case here. Okay, do you have any doubt how this represents a plane? I can maybe explain that. If not, I can proceed, right? Is it okay? Okay, then yeah, I mean, so these represents planes in 3 dimensions, right? So that's pretty straightforward. Now there will be many scenarios here. It's not in this case we have we can have only these 3 scenarios in the 2-dimensional system, but in 3-dimensional system you can think of many different scenarios, like all these 3 planes will be can be parallel to each other, right? So I mean, for example, they'll have all the same normals. So you know what normal is, right? Normal is a perpendicular on a plane. Yeah. So if all the 3 planes have same normal, they'll be parallel to each other, right? And in this case, you'll have no solution for these systems of equations. Okay. Similarly, you can have 2 planes having same normal. That means 2 planes parallel, and another plane cutting through them. In this case also, you will have no solution, because they are not I mean, you don't have a unique set of points for them, so it's also a no solution case, right? Then they can all meet at a single line, Okay, they can be oriented such a way that they will meet at a single line like this common line. Okay, and at least they are meeting somewhere, right? All the three are meeting somewhere. Like in these first and two cases, they are not both the three planes, all the three planes were not intersecting each other, right? Here in the first case, none of the three were intersecting. In the second case, one was intersecting the other two, but the other two were isolated. But here all the three are intersecting each other, but on a line. So that's why you have a infinite set of points. Line is what? A line is infinite set of points, right? So you have infinite solution here. Now this also one thing happen. For example, in the fourth case, what's happening here? All the three are intersecting, right? But I mean, all the three are intersecting each other, but on a different lines, right? So in this case also, you have infinite solution. Now we come to the and you can think of many combinations of planes, right? I mean, these four are not just enough. I mean, you can have any orientation. It's just on your imagination. It just depends on your imagination. What can you imagine with three planes? Okay, every scenario will be there for these different coefficient and different k values. So now in the fifth case, what you get is that all the three planes intersect at a unique point. Okay, they are oriented in such a way that they intersect at a unique point. Now only in this scenario you will have a unique solution. Okay, only in this scenario. Any other scenario you can imagine, you won't have a unique solution. Understood? Vignesh, is that clear? Is that what you wanted? Yeah, okay. So okay, I'm glad that you understood. So now so moving on to this week's content, I'll solve some examples so that you can get to know how to solve this week's assignment. Okay, so the first example that I'll solve is Gauss elimination with partial pivoting. So if you have seen the lectures for week 3, you know what partial pivoting is, right? Partial pivoting means simply the row exchange, right? So row exchange. Complete pivoting is just column exchange plus row exchange, and partial is row exchange only. Okay, so we have this equation here. We have this so this matrix comes from a system of equation. I mean, in the last session I showed how to get this A B matrix from a system of equation. So I didn't wrote the system of equation. I just I took a shortcut and wrote this augmented matrix. Okay, so to solve this with Gauss elimination and using partial pivoting, so what partial pivoting does is it make your life easier. Okay, and there one more thing that partial pivoting is helpful, where it's helpful, that I will tell you at the end of the solution. But it simply makes convenient to solve the equations. So let's start with Gauss elimination. So the first step in partial pivoting is you look at the column 1 and see which is the largest element here. Okay, so you see the row 2 has the largest element for column 1. So what you need to do is that you must interchange it with the row 1. Okay, that's the first step in partial pivoting. So this is the step where you change the rows, so that this is the row 2 will become your pivot row. Okay, so what this will give you, sorry, this will give you 1 2 1 0 and 1 0.02, 0.01, 0.01. Okay, and the rest will be the same for now. 1, 4, 0, 0, 100, 200, 800. Okay, and this is step 1. In the step 2, you have the simple the same Gaussian elimination technique. So what we do there, we take rho 2, rho 2 goes to rho 2 plus alpha 21, alpha 21 rho 1, right? And alpha 21 is just minus A21 by A11, right? And here alpha 21 will be so the A21 now is 0.02 and A11 is 1. Okay, so this is your A11 and this is your A21. So with this step, so I mean this is a simple arithmetic. So with this step, so this is the step where you do the row exchange, and in the next step you do the Gaussian elimination, right? And you get this matrix. So when you do this, R2 goes to R2 plus alpha 21 R1, you get this matrix, right? So as you see, what was our alpha 21? Our alpha 21 was minus A21. A21 was 0.02 divided by. So as you can see, for the A22, you will have 0.01 minus 0. Minus 2 into minus minus 0.02 into 2, so this will be minus 0.03. Similarly for this element you have simply, because here the A23 is 0, so you will have just minus 0.02. Okay, similar, and you do the same for this element here, and you will get 0 because you have 0.02 minus 0.02 is equal to 0, right? It's pretty straightforward, you must know. I solved many examples in the last session also. Now after you get this matrix after Gaussian elimination, so here you don't perform this operation as you used to do with the naive Gaussian elimination, alpha 31 R1. This is not done here, okay? It will be done in the this before doing this step you need to check whether the new matrix requires the pivot exchange, partial pivoting or row exchange. Okay, so you see in the next step, in the step suppose 2, you see that this row that we got here, again for column 2 you see this row 3 has element has larger value than the row 2 element, right? So we need to exchange these two row here too, and so this is another step of partial pivoting where you exchange R2 and R3, right? So and you get this matrix, and then again we have to make sure that this elements goes to 0, so then you do the Gauss elimination like before, because remember at the end we need our upper triangular matrix, so these elements need to go to 0, right? So in the next step we do this again Gaussian elimination. Here what we how we do the Gaussian elimination, we have this between R3 and R2, right? So R3 goes to R3 plus alpha 32 R2, okay? And so here alpha 32 will be minus A32 by A22, alpha minus A32 is just 0.03, so it will be plus, and it's just 1. Okay. Now with this operation, the third row will be converted like this, right? All the elements will be positive, and we'll get a 0 here. If you have any confusion at any step, you can ask. Okay, maybe if I'm skipping some steps, you can ask if you don't understand. But I hope you understand, because I solved 4 examples last time on Gauss elimination, so I expect that you don't have any confusion on the steps, right? Yeah. So okay, anyways, so you get this third row like this. Now again you have to see whether this third row and fourth row needs the partial pivoting, right? And as you can see, this value is far bigger than this third row value, so we need to do this exchange of row before going on to the next Gaussian elimination and turning this to 0. Okay, so we do this row exchange R3 and R4, right? And you get this matrix. Okay, now all we have to do is turn this to 0, and then we can use the back substitution to make this matrix upper triangular matrix, and to solve this matrix basically. Okay, so in the Gaussian elimination, what we need to do is R4 goes to R4 plus alpha 4 3 R3. Okay, and here alpha 4 3 will be minus, sorry, pencil is not working correctly, minus A43 by A33, right? Which is just A43 is minus 0.04 divided by 100, right? It will be very low value, like 0.0004. Okay, so that we do here, and we get this matrix here. Okay, so 200 minus sorry, R4, yeah, so this will be 0, as you can see. This term will goes to 0, because you will have 0.04 and minus, yeah, minus what we got here, 0.0004 into 100, right? So it will just be 0.04, and it's negative, so it will be 0. Similarly, you will get minus 0.05 if you do the same operation on third column, and you will get minus 0.2 if you do the same operation on this fourth column. Okay, so as you can see, we have converted our matrix here into a upper triangular matrix, right? These are zeros, and only we have diagonal and upper triangular matrix. So now we can use our same old back substitution method to obtain the solution, right? So we can start from below. We will have just something is wrong. No, there's a mistake here. It should be minus 0.05x is equal to minus x4 is equal to minus 0.2, right? And so your x4 will be 0.2 by 0.05. Okay, this gives 2 zeros here, this gives 1 0, it will be 4. Okay, so the answer was correct here, but equation written was wrong. Okay, similarly from the third row, you'll have this equation, and it will give x3 to 0 from the because you have x4 here 4, so 200 into 4 will be 800, and so x3 will be just 0. And from the second row you will have this equation, putting x3 and x4 you can get the x2, which will also be 0. And then from the first row you will have this equation, and you have x2 and x3 you can put here, and you can get x1 is equal to 1. Okay, so the solution matrix will be simply 0 1 1 0 0 4. Okay, so this is how you do the partial pivoting and solve the equations using Gaussian elimination. Now as I said, it's very simple to I mean it's make our life easier. If you like, if you can try and solve this same system of equation using the hello, someone is speaking. Okay, so I was saying that if you can go ahead and solve this using the naive Gaussian elimination, like I showed you in the last live session. You will see that the calculations will be very very lengthy, and you will need to use calculators, and it will be very difficult rather than this solution that I showed you. Okay, and but there is one more thing that is because of that we use the partial pivoting, is that pivoting help reduce the rounding errors. Okay, because in this when you do the row exchange and you exchange the larger element with the smaller element, and when you do this Gaussian elimination step, you are less likely to add or subtract very large or small number. Okay, so in that way when you add or subtract a large number, you need to do rounding, right? You cannot take all the digits that you have after decimal, so that this algorithm saves you from that, and you will have a very less rounding error. This might not be visible in this example, but there are many other examples. If you have like if the difference between these two elements will be very large, then you will have this scenario where rounding errors will come, and this partial pivoting will save you from that. So that's another reason we use the partial pivoting. Okay, so any question on this solution? Okay, thank you. So let's go on to our next example, and here I have put up a problem on tridiagonal matrix, and I'll solve it using the Thomas algorithm. So you guys know Thomas algorithm, right? So it's all these different algorithms are very similar. There are little differences between them, and all these little differences are because when you solve so that our computer do it more fast, so we skip some steps, that like you can solve any of these equations using any of the methods, but which equations will be efficient with which method, that you need to decide, and that's what these lectures are about. Okay, so as if you have gone through the lectures, you must have known that this Thomas algorithm saves you saves you time and make the calculations shorter. Okay, because it doesn't involve many useless multiplication and division that you will have in simple Gaussian elimination or other algorithms for tridiagonal matrix. Okay, so what Thomas algorithm says is that so in the first step of Thomas algorithm, again you have this system of equation. Okay, and where there is blank, there are zeros. Okay, so maybe I'll write it then explicitly. So first of all, what is tridiagonal matrix? So tridiagonal matrix are those matrices which have three diagonal rows. For example, there will be a main diagonal, there will be a super diagonal, and there will be a sub diagonal. Okay. So for example, here this row is our super diagonal, this is our main diagonal, and this is our sub diagonal. Okay. And and rest of the elements will be 0. So that's what we called a tridiagonal matrix. Okay, these type of matrices appear in various places. If you if you go and model some physical situation like transfer of heat from a slab, like in the lecture there was an example where there is a metal slab, and at one end it's kept at 100 degrees Celsius, and other end it's emitting 25 degrees Celsius temperature. So if you divide this in various blocks and you discretize the differential equation, you will end up with a matrix looking like this tridiagonal system. So it's very important to know how to solve these tridiagonal matrices using this Thomas algorithm. You can solve it in many other ways, but Thomas algorithm is the most efficient ones. Okay, so yeah, let's try to solve it. I don't know how much time we have, but let's see how far I can go. Okay, so here the first step is to divide the first row 1 by a11. Okay, so that we'll have a11 is equal to 1. Okay, this is the first step. Then in the step 2, what we do is if we want to make this element here a21 0, we want to make this one 0. How would we do that? We'll just do this same Gaussian elimination step. So R2 will be R2 and alpha 21 R1. Here alpha 21 will be what? Alpha 21 will be minus a21 by a11. But see, a11 is just 1, right? So it's minus of alpha 21. Okay, and alpha 21 in our case is minus 1. So if you see here, step 2, okay, let's go step by step. Okay, so it's just minus of a21. Okay, alpha 21 will be a21 minus a2. Okay, so let's do this first step 1 and step 2 for this matrix here. So when you divide R1 by a11, what will you get? The new matrix. So 2.04 divided by 2.04 will be just 1, and minus 1 minus 1 divided by 2.04. Let's see what it will be. So I already have done some calculations so that we can have time. So it will be minus 0.49. Okay, so it will be minus 0.49, and the rest elements will be the same, and you will have and also you have to divide this B matrix also. Do the same operation as you are doing here with the B matrix also. So 40.8 divided by 2.04 will be just 20. Okay, so it will 20, and other elements will be same, minus 1 0 and 0.8, 0 minus 1 2.04 minus 1 0 0 minus 1 2.04 0.8 200.8. okay. Now in the next step, what you need to do, you need to perform this. R2 goes to R2 minus a21 R1, right? So what happens in the first column, you have R2, at R2 you have minus 1, and you have a21 as 1, and you have R1 as 1. In R1 you have 1. Okay, so it's just sorry, did I do some mistake? Oh, yep. uh, Sorry, what did I do? Minus A21 minus A21 is, oh sorry, A21 is minus 1, right? Yeah, so you have minus minus plus minus 1 plus 1 is 0. Okay, so and then again for this row 2 you have 2.04 minus of minus 1, and at R1 you now have this value, right, which is minus 0.49. okay, so this is 2.04 minus minus plus one more minus 0.49. okay, and it will be 1.550. okay, you can check it. So what will we end up getting? So let me erase this. So with this step you will get a matrix like this. So you have 1 minus 0.4900 and minus sorry, this is 0, this is 0, this is 1.550, and the rest elements will be same because you have 0 here, so rest elements will not be changed here. Also the below elements will be same because we are not doing anything to them. And for the B matrix in this step, what you have, you have let's say here you have 0.8 and minus of minus 1 into 20, right? So it will be 0.8 plus 20. Am I right? 0.8 minus 20, yeah. So you will have 20.8. So there you have 20, you have 20.8, 0.8 and 100.8. okay, so let me write it again here for your reference. So after the end of first and second step, you will have minus 1, minus 0.4900, 1.550, minus 1, 0, and you have the same matrix, which is 0, minus 1, minus 2.04, 2.04, 0, and you have 0, 0, 0, 0, minus 1 and 2.04, right? And for the B matrix you have 20, 20.8, 0.8, 100.8. okay, so we are done with our first and second step. Now for the step 2 and 3, okay, so for the step 2 you need to repeat the first and second step, but you just change row 1 to row 2, okay, sorry, row 1 to row 2 and row 2 to row 3. okay, whatever we did in this step, we just we just shift our focus on row 1, row 2 and row 3. okay, so now you have to divide row 2 by by A22. okay, and for a step, let me write more clearly. So divide R2 by A22, and in step 3 in step 3 you do this. R3 goes to R3 plus alpha 3 to R2, where alpha 32 will be minus A32 like before. Okay, so you see here and in this step just there is interchange of 2 to 1 and 3 to 2. Okay, and everything will be same. Okay, so yeah, let's do it. So for the step 2 we have to divide this root R2 by A22, which is 1.550. so let's do that. Our first above matrix will be same, above row will be same. Here will be 0, here you'll have 1 because you're dividing this it itself, and then you'll have minus 1 divided by 1.550, and it will give you minus 0.645. okay, so here you'll have minus 0.645. this is 0, and the below term will remains the same. 2.04, 0, 0, 0, minus 1, 2.04. Now here you have 20, and you have to divide 20.8 by 1.550. okay, I don't have this calculation, so let me use my calculator quickly. Sorry, edit. I think I have to minimize. Okay, yeah, so we have to divide 20.08 by 1.550, right? 20.8 divided by 1.550. So it will be just 13.419. okay, so it is 13.419, and you have the same values as before. Okay, so this is after step 2. Now you have to perform this third step to this matrix. Okay, where R3 goes to R3 minus A3 to R2, right? R3 goes to R3 minus A3 to R2. okay, it is straightforward. This element will be 0, right? Because you have minus 1, and A32 is A32 is minus 1, and you have R2 is 1, so this element will be just 0. And for this element you have 2.04 minus, what is A32? A32 is minus 1, and at row 2 you have minus 0.645, so you have 2.04 minus of minus 0.645, and this is just 1.395. okay. And also in the last step you have for this B matrix you have 0.8 minus of minus 1, and at the row 2 you have 13.419. okay, and so this is 0.8 plus 13.419. so just I'll add 0.8 here, which is 14.219. okay, so at the end of step 2 and step 3, what you will have, 1 minus 0.49, 0, 0, 0, 1 minus 0.6450, 0, it will be 0, and this one will be converted. Oh, wait, let me write bigger. Okay, 1 minus 0 0 0 0 1 0 0 this is 0, this will be 0, and this one is 1.395, this one is 0, and below row is just the same, 0 0 minus 1 2 4, and this B column is 13.419, 14.219, 100.8. okay, so this is what you will get after step 4. okay, now we have to perform another set of 2 steps, step 5 and step 6. okay, in step 5 you just change 2 to 3 in the previous step, and the step 6 you just change 3 to 4. So if you know if you have done some computer coding or something, so look how easy is it. You have to just write an algorithm for first 2 steps, and you just iterate it over the next if you have 4 equation, you just if you have 4 equation, you iterate on the 3 steps, okay, and just increase the iterator by 1 value. okay, so that way, this is very computer efficient technique to solve tridiagonal matrix. okay, so yeah, so then so you need to so we have just this last 2 steps we have to do. So let's do, I think we have 10 minutes more. okay, because I started late, so yeah, let's do it. okay, so first step 5, what I'll do, I'll have to divide R3 by what? By 833, right? This value. And in the step 6, I have this Gauss elimination, which is 4 goes to R4 plus because since alpha 4 3 is just 1, it is just minus of A4 3, right, as we have before. It's R3. okay, so you will notice this same thing, just instead of 3 you have 4, instead of 2 you have 3. It's very easy. So let's perform these steps for this matrix. Sorry, let me erase this so that I can fit it in the slide itself. So in the step 5, I'll divide this by this row 3 by A33. okay, so what it will give us? It will give us, let's keep the upper rows same. Here you will have 0 0 1 0, and in the B side you will have 20, you have 13.419, and you have to divide 14.219 by 1.395. okay, so let's quickly do that. We already have 14.219 on the calculator. Just divide it by 1.39 5. So it is 10.193, and you have 100.8. Okay, so step 5 gives you just one value here and this 10.13193 value. Now on the step 6, quickly we can see what we have here. R4 minus A not alpha A43 R3. Okay, so for this this will be 0, right? Because you already have 1 here, and minus 1 plus 1 will be just 0. And for this element in the fourth column, you have 2.4 minus of A43 is just minus 1, and R3 is 1.395. Okay, what it is? Sorry, not 0. It is wait. I made some mistake. What is it? Wait, let me see. It's not going. Something's glitching. Yeah, it's okay. So 2. We have 2.04. Yeah, 2.04. Okay, so it's just 2.04 plus 1.395, right? Let me add this 2.04 plus 2.04 plus what is done? It's adding it to itself. So 2.04 plus 1.395. You have 3.435. Okay, and for the B element here, you have 100.8 minus of minus 1 14.219, and this is 100.8 plus 14.219. What will be the value? Let's see, 100.8 plus 14.219 is 115.019. So finally, after step 6, what you have in this in the matrix is let me erase this. I think it's well over time. Let me just finish quickly. So after step 6, we will have 1 minus 0.4900, 1 minus 0.645, 0, 1.395, 0. This will be 0, and here you will have 3.435, and in the B matrix you will have 20, 13.419, 14.219, and 115 point 019. Okay, yeah. So now it's pretty straightforward to solve this because you have you have all these elements 0. You can write you can do the back substitution as you do in the Gauss elimination, and you can get the X matrix easily here. So let's not do that because we are well over time. And so do you have any doubt on this example? I think weakness. Okay, it's fine, right? Okay, then so you have any question or doubt on today's session, or if you have any general question, you can ask about the lectures. Okay, thank you then. Thank you for joining. I'll close the meeting now. Okay, thank you.